Hey everyone, this is EddieDoesMath. Welcome to my channel. I've got a gift for you in the description below. If you click on the link, you'll get access to a problem set of 30 practice SAT problems. Really excited to show you those. And even more excited to bring to you today everything you need to know about triangles on the SAT. It's time to lock in. Interior and exterior angles. Let's first prove how many degrees in a triangle. So if you sum up the interior angles here, you will notice that we get 180 degrees. But where do we get that from? Well, if we draw a little line that's parallel to this base right here, and we extend this a little bit as well, we recognize that if we call this B, and let's use different colors here, and we call this A, then by alternate interior angles, this will also be A. And if we call this C, by alternate interior angles again, this will also be C. Therefore, A plus B plus C equals 180, and that's how we know the sum of interior angles of a triangle adds up to 180 degrees. Now, for exterior angles, let's take this exterior angle right here and call this X. Well, X plus some C is going to equal 180 degrees. But we also know that if we have some A and B, A plus B plus C is also equal to 180 degrees. So if we wrote these two equations down, A plus B plus C is equal to 180 degrees, and we also know that X plus C is equal to 180 degrees, what do you notice? A plus B and X must be the same in order for the remainder of these equations to maintain that balance as well. So that's how we know that the exterior angle of a triangle is equal to its non-adjacent angles added up. Now let's use this on some practice problems. If AB is equal to AC, so if these two sides are equivalent, meaning this is an isosceles triangle, find y in terms of x. So y in terms of x means isolate the y, there will be something in front of that x right there. Okay, well, in an isosceles triangle, the base angles will be equivalent. So this angle will be equivalent to this angle right here. So we know that 3y minus x is our exterior angle, so it will be equivalent to the non-adjacent angles added up. And my non-adjacent angles are y plus 2x. The other one is also y plus 2x. So we can multiply this by 2, y plus 2x right here. I almost wrote 2y plus x. Y plus 2x. Go ahead and distribute. So we have 2y plus 4x. And on the other side, we have 3y minus x. We can subtract 2y on both sides, add an x to both sides, so y is equal to 5x, and there is y in terms of x. Next question, if AB is equal to AC, so if AB is equal to AC and is equal to CE, we have two isosceles triangles here. ABC is an isosceles triangle, and ACE is an isosceles triangle. So we know a couple things. We know that this angle right here, I'll post it in green, this angle and this entire angle are equivalent. And we also know that these two angles will be congruent because of this isosceles triangle. Find the value of x. All right, let's check this out. In this ACE triangle, if I were to redraw this here, it looks something like this, and these two are equivalent. I've tried to draw it to the best of my ability here, A, C, and E. We know that this is 40 degrees. Well, 180 minus 40 is 140. So these two angles are equivalent. We know that each of them will be 70 degrees. So that's what I'm going to write right here, 70 degrees and 70 degrees. Well, on a straight line, I know that a straight line creates a 180 degree angle. Subtract 70. That'll give me 110. And you kind of see where this is going now. If this is 110 plus that 60, that's 170, leaving just 10. Leaving just 10 degrees right here. So my entire green angle right here will be 40 plus 10, which is 50 degrees. We know that these two angles are the same, so that's also 50 degrees. I know by my straight line right here, 60 plus 120 gives us that 180. 120 plus 50 is 170, leaving x is equal to 10 degrees. What a great problem. Talking about angles here. Now, equilateral triangles. What is the length of EC? So we want to find this x right here. Now, since we know this is an equilateral triangle, all these angles are equal to 60 degrees. And this all together is also 60 degrees. And we can tell because we have 30, 15, 15, adds up to 60. Now, we're given the side lengths, 20, 20. So we know BC all together is 20. Well, 20 minus 14 is 6. So x will be the same distance as x here. So 2x is equal to 6. Therefore, x is equal to 3. And there's your length for EC. Find the value of y. Again, an equilateral triangle. So we know this entire angle A will be equal to 60 degrees. So if you go 2x plus x, that'll equal 60 degrees. Let us solve for x. X will equal 15. Okay, so if x is equal to 15 degrees, what will my y be? Well, 2 times 15 is now 30 degrees. And since we have, an isosceles triangle here, because we know that x and x are the same, the base angles will also be the same, y degrees and y. So 2y will equal 180 minus 30, which is 150. So y by itself is equal to 75 degrees. Very exciting stuff. All right, now let's move on to area of triangles. Find the area of the following triangles. Well, the area of a triangle is, we all know, 1/2 base times height. Some of you know it as length times width divided by 2. Any of those will work as long as you have that same structure. So base is 7, height is 4. So the area will be 1/2 base times height. We have 7 times 4 is 28, divided by 2 is 14. And don't forget your units of measure, centimeters squared. Same idea here, 1/2 times base times height. 12 divided by 2 is 6, times that 5 is 30 centimeters squared once more. And don't get confused just because we have different looking triangle here. It's still the same. The base is 10, the height is 5. So 5 times 5 gives us 25 centimeters squared. Don't get thrown off by that. This 3 does not matter, right? If we included the 3, then we'd actually be finding the area of this bigger right triangle, right? But because this 3 is not included within this blue bordered triangle, we only take 10 as our base and 5 as our height. Let's check this out now. So the base here, we'll be looking at the x values. 1 to 5 is just 4. And then now we look at the y values. The y values will give us the height. 2 to 8 gives us a height of 6. So if we were to find our area here, we'll have 1/2 base times height, and that gives us a nice little 12. Area of this triangle is 36 centimeters. So we know that the area is 1/2 base times height, and we're given this is 36. Again, this 6 centimeters has nothing to do with this problem. Maybe it can figure out this empty space, but doesn't matter in regards to the area of this blue triangle. So let's solve for h. Half of 18 is 9. So if 9h is equal to 36, therefore h is equal to 4. Don't forget your units of measure, centimeters. I would put units squared here as well. All right, another area of triangles. The figure below shows 4 connected congruent equilateral triangles. Given that the figure has an area of 16 radical 3 and a perimeter of p, what is the value of p? So I want to figure out the perimeter of this triangle, and I know that the area of this entire diagram is 16 radical 3. Well, I know that these 4 are congruent. Therefore, the area of just one of them will be 4 radical 3 if I divide 16 over 3 by 4 to get just one of these triangles. Now, I know each of these are equilateral triangles. So if I called, let's say, this side length x, this would be x, and this would also be x. And I know that the base angles, or all the interior angles, are worth 60 degrees. And I can use my 30, 60, 90 triangles here. We'll be covering special right triangles in a little bit. But in case you didn't know, we can use 30, 60, 90 triangles and a little, proportion here, relationship. We know that this length right here will be x over 2. Therefore, the height will be x radical 3 over 2. and then we can find our area. Area is half of base times height. That gives us x squared radical 3 over 4. We're given the area is equal to 4 radical 3. So you can see right off the bat, the radical 3's will cancel out on each side. Multiply both sides by 4. In other words, x squared will equal 4 times 4. So x will equal 4. Now, we're not done with the problem. We want to find the perimeter of this entire figure. So if this is 4, then this is 4, 4, 4, 4, and 4. We have 1, 2, 3, 4, 5, 6 of them. So the perimeter will be 6 times 4, which is 24. And we're not given any units here, so we can leave it just like that. That was a fun one. All right, Pythagorean theorem. By constructing a square on each side of a right triangle, we recognize a relationship / pattern between the areas of these three squares. So 3, 4, 5. 3 squared is 9. 4 squared is 16. 5 squared is 25. Notice that 9 plus 16 is 25, and that's why the Pythagorean theorem works. A squared plus b squared is equal to c squared. Just like this. Let's try out some cool problems now. Find the missing length of x. One way we could solve this is to solve for the entire length here, the entire long side here, and then the long leg of this smaller triangle and subtract the two. So let's redraw these triangles. Here we have 15, here we have 5. Let's solve for this unknown. This unknown will be the square root of 15 squared minus 5 squared. Now, where did I get that from? I got this from plugging in 5 squared plus our unknown squared is equal to 15 squared. I subtracted 5 squared from both sides and then square rooted to get whatever that empty box will be. This equals the square root of 15 squared is 225 minus that 25 gives us 200, which is 10 radical 2. Now let's figure out this shorter length of the other triangle. So if we have another right triangle here, 7 and 11, don't forget this is in centimeters. This side will then be square root of 11 squared minus 7 squared. And that's equal to 121 minus 49. That gives us square root of 72, which is 6 radical 2. Now, if you're struggling with simplifying radicals, you need to work on your multiplication tables or just prime factorizing, right? Prime factorizations. 72 is 36 times 2, and the square root of 36 is 6. That's where we got that 6 from, and the 2 stays within the radical, centimeters. So x will simply be 10 radical 2 minus 6 radical 2, and we get a very nice answer of 4 radical 2 centimeters. Let's solve for x in these triangles here. Again, set up your Pythagorean theorem or recognize some patterns. We notice 3 and 4. Now 3, 4, 5 is one of our special right triangles, so that's how we know x is equal to 5 right off the bat. But if you didn't know how to do that, you can set this up like this. 3x squared plus 4x squared is equal to 25 squared. Now 25 squared is 625. We get 9x squared plus 16x squared here. 25x squared is equal to 625. Therefore, x squared is equal to 25, and x is in fact equal to 5. Let's check this one out. This one might not be as simple as what we did in this one. So let's set up our Pythagorean theorem. 2x squared plus 5 radical 5 squared will be equal to 3x squared. This gives us 4x squared plus 25 times 5. That gives us 125, and we have 9x squared right here. Subtract the 4x squared from both sides. I'll be left with 5x squared is equal to 125. Divide both sides by 5. Got a 25. X is again equal to 5. So x happens to be 5 for both of these. Now, the Pythagorean theorem is the distance formula. Let's check this out. So a is negative 2 comma 3. So negative 2 comma 3 will be somewhere around here. Then 4 comma negative 1 will be somewhere around here. Right? Further to the right, but down from 3 to negative 1. So this line right here that we can draw, that's going to be our distance d. Let's figure out how we can figure out this distance. Well, we can draw a little right triangle with a right angle, the distance in the y direction, the difference in the change in the y direction will be 3 to -1. That's a change of 4. From -2 to 4, that's a change of 6. So I can figure out d by doing 4 squared plus 6 squared is equal to the distance between these 2 points squared. And guess what? I can take the square root of both sides. 4 squared is 16. 6 squared is 36. And that gives me the square root of 52. That's divisible by 4 because it's 4 times 13. We get 2 radical 13. So what do we just prove? The distance is the square root of the other two changes in x and y squared. So distance formula is the square root of the change in x squared plus the change in y squared. Many of you might have seen it like this: x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared. But I'm here to tell you that you don't have to have this in this particular order, because when we square it, whatever this number is, positive or negative, will become positive anyway. So you don't have to worry about the x sub 2 and x sub 1, the order in which they come from. You just need to find the difference between those two values for in both the x and y direction. And it's basically the Pythagorean theorem. Let's check this one out. An isosceles right triangle. Isosceles right triangle will be a right triangle that has two equivalent sides. So the legs must be equivalent. The hypotenuse can't be one of the equivalent angle or sides, because the hypotenuse is always the longest side, right? The longest side. So the area is 32 centimeters. Okay, let's call this length x. Therefore, this length would also be x. So the area of this triangle will be 1/2 base times height. That's x squared. And that's going to equal 32. Multiply both sides by 2. We get x squared is equal to 64. X will be positive or -8. But because we're talking about distances here, got to be that positive 8 centimeters. We're not done. We have to figure out our hypotenuse. If x is equal to 8, then by 45, 45, 90 triangles, we know this is 8 radical 2. But let's say you don't know that yet. Let's set up a Pythagorean theorem. 8 squared plus 8 squared will be equal to the hypotenuse squared. 64 plus 64 is 2 times 64. And we can take the square root of 2 times 64. Notice how I left it like this, because the square root of 64 is 8. So we get 8 radical 2 is equal to h. Don't forget centimeters. Centimeters. Units of measure, very important. Okay, Pythagorean theorem. Let's look at some Pythagorean triples. If we have 3, 4, we know this is the most common one. We'll have 5 centimeters. You can solve it by using the Pythagorean theorem here. We also know a very common one, 5, 12, 13. So some must-know Pythagorean theorems. 3, 4, 5, must know. 5, 12, 13. Oops, I put a comma there instead of a dash. These aren't minus, by the way. These are dashes. 5, 12, 13, also super common. And any multiple of these Pythagorean triples will work. So 6, 8, 10 works. 10, 24, 26 works. And you get the gist, right? You can multiply by 2, by 3, by 4, by 1/2. All of these work. Any multiple of these Pythagorean triples will work. Another popular one will be 8, I believe, 15, 17. Let me know down in the comments if you know that one. And then 7, 24, 25 is another one as well. Fun stuff. So there are some cool relationships other than the Pythagorean triples that we observe that occur repeatedly in a constant pattern. We recognized here that when we had congruent sides, we can multiply this 8 by radical 2 to get to the hypotenuse. Now, does this always work? And it just so happens it does. When the right triangle is isosceles and the legs are congruent, that means the opposing angles are also congruent. This is what we will call our 45, 45, 90 triangle. And when we have something like this, we have some box here, then this is also going to be box. We can multiply whatever's in that box by radical 2 to get to the hypotenuse. In reverse, if we had box over here, then the legs will be box over radical 2 and box over radical 2. Because if we multiply by radical 2 going from the leg to the hypotenuse, then going in reverse, we must divide by that radical 2. So that's why I did it in different colors here. Another special right triangle is when we have a 30, 60, 90 triangle, and this always happens. This always works. If we have the shortest leg, which is opposite of the shortest angle, the smallest angle, we can do anything with this triangle. We can solve the other sides. If we have a 30, 60, 90 triangle, 30, 60, 90 triangle, we can multiply the shortest leg by 2 to get to the hypotenuse and multiply the shortest leg by radical 3 to get to the longer leg. Now that's all you have to know, but you also have to know how to go in reverse, right? From here to here, we've multiplied by 2. From here to here, we've multiplied by radical 3. So if we were to go in reverse, we would divide by 2, and in reverse, we would divide by radical 3. So if you know just one length of a 30, 60, 90 triangle, you are able to figure out the other two side lengths, which is pretty awesome. And that's what we call it, special right triangles. Let's solve some questions and problems that involve these special right triangles. It actually becomes really, really cool. All right, lock in. Here we go. In the figure below, if AB is parallel to CF, this entire base, what is the length of line segment BC? So that's X. All right. Well, special right triangles, Pythagorean triples coming up right here. 5, 13, we know this is 12 right off the bat. This is one of your Pythagorean triples that you must know, right? 3, 4, 5, and then there's 5, 12, 13. Now, since we know that AB and CF are parallel, I also know this length BD will be 12. I also recognize CF is a line, so since this angle is a right angle, I know this angle will also have to be a right angle because 90 plus 90 is equal to 180, this line. All right, so we have 45 degrees. This will also be 45 degrees. Guess what we have? We have a 45, 45, 90 triangle. That means this has to be 12, and X will be 12 times radical 2. And that's it. You could solve it really quickly now. Find the value of X. We have an equilateral triangle. How did I recognize that right off the bat? I noticed a triangle with 60 degrees for 2 of the angles. The other angle must be 60 degrees because we know that the 3 interior angles of a triangle add up to 180. And since this is an equilateral triangle, since all the angles are congruent, the side lengths must also be congruent. Now I recognize 10 and 8 because this is our 3, 4, 5 triangle. X is going to equal 6 because 6, 8, 10 is a multiple of 3, 4, 5. It's as simple as that, y'all. Let's try this one. What is the ratio of BD to DC? Ooh, okay. So this one's going to be slightly more challenging because we're not given any lengths. We have to set these lengths to each other, basically. So let's call DC Y. So we're trying to find the ratio X is to Y. So if we can write Y in terms of X or X in terms of Y, we'll be able to solve this out. Okay, let's take a look. Our bigger triangle, ABC, our bigger triangle, ABC, again, when in doubt, redraw the triangles that you see. This is 30 degrees. So therefore, if, let's bring in, I don't really want to bring in another variable here. Let's see what we can do. Let's call this box, right? Let's call this box. And so then, if this is box, then this entire side will be box radical 3. Because this is a 30, 60, 90 triangle. We don't have to worry about AC. Now, in that same smaller triangle, this is also box, right? They share that side AB. A, B, D. All right, now I see the flow here. If this is 60 degrees, this is going to be 30 degrees. So this right here is going to be box over radical 3 because this is our shorter side. The shorter side times radical 3 will get us to this longer leg. So in reverse, we divide by radical 3. So what do we just find? x is equal to box over radical 3. Y we don't know yet, but we know that x plus y is equal to box radical 3. All right, so I can write y in terms of x. I can write y in terms of x if I subtract x on both sides. If I subtract x on both sides, I'll get y is equal to box radical 3 minus x, which will be box radical 3 minus box over radical 3. What I did here is I substituted this for that x. This for that x right here. So now I can put x is to y. I can say x is box over radical 3 is to y, which is box radical 3 minus box over radical 3. Let's do something here where we multiply everything out by a radical 3, both sides. So what we're going to do here is we're going to multiply both sides out by the denominators that we see, which is radical 3. So on the left, I get box, which we're just going to call 1 at this point because it's going to cancel out. Radical 3 times radical 3 is 3, so we have 3 box minus a box, and guess what we get? We get box is to 2 box. We cancel these boxes out, we get 1 to 2. So it just so happens, whatever x is, y is going to be 2 times that. Pretty cool what we just did. In the figure below, find this length of segment AB. So here's x, that's what we want to find, if segment BD is 10. So all this right here is going to be 10. Now, many students get stuck on these types of problems because they don't realize that BD is a straight line, right? If this is 30 degrees, we know that a right angle is 90 degrees. Add those up, that's 120. So this has to be 60 degrees. What have we just found? A 30, 60, 90 triangle here. The hypotenuse is 8, therefore the shortest leg is 4. And guess what? If the whole BD is 10 and CD is 4, then what is BC? 6. 10 minus 4 is 6. Or in other words, 6 plus 4 is 10. That's how we know BC has to be 6. And because x is the shorter side, this is our 60 degree angle. 6 is our longer leg. I'm going to divide 6 by radical 3 to get to x. And if you really want to rationalize the denominator here, you can multiply both top and bottom by a radical 3. You get 6 radical 3 over 3, which is 2 radical 3. Just like that. Beautiful problem. All right, another one. In the figure below, find the length of segment AB. So this is what we want. We recognize right away, 45, 45. So if we know this one, we'll know that one right away. We have a 30, 60, 90 triangle here on the right attached. So if this is 12 radical 3, that's the longer leg. I'm going to divide by radical 3 to get to my shorter leg. That'll be 12. And I need my shorter leg because if I have my shorter leg, I can multiply it by 2 to get to the hypotenuse. 24, then x also needs to be 24. Kobe. Solve for the length of AC. I'm looking for x here this time, and this is kind of a trick problem, but let me walk you through it step by step. I don't know any of the angles here, so there's really no way I can solve for this because I don't know this angle either, but I do know one thing. I recognize that these two sides are the same. So what does that mean? That means the base angles, the opposing angles must also be the same. So I see the 30 degrees and I'm like, oh, I know how to use 30, 60, 90 triangles, but I don't see a right angle. Let's create one. We can create a perpendicular bisector of BC here to create right angles here. And so now if I know that this is 60 degrees. So if this 8 radical 6 is my hypotenuse, my shorter leg will be half of that, 4 radical 6. In order to get from my shorter leg to my longer leg, I'm going to multiply by radical 3. So this will be 4 radical 6 times radical 3. But we're going to have 2 of these for the entirety of x, because 4 radical 6 times radical 3 is just from here to here. We need a whole nother one of those. So x is going to equal 2 times 4 radical 6 times radical 3. Now, 6 times 3 is 18. And this becomes really fun here. The square root of 18 is the square root of 9 times 2, which is 3 radical 2. So if 8 times 3 radical 2, which is 24 radical 2. And that's a beautiful problem right there. Find the value of h. So h is right here. That's what we're looking for. We don't know much about this problem, except we also need to know that this is a perpendicular right angle right here, perpendicular line right here. If this is 30 degrees, this is 60 degrees. Therefore, this is 30 degrees. The SAT loves doing stuff like this, so keep an eye out for all that. So if this is 4, then I know that this longer leg will be 4 radical 3. Well, now I know that this is 4 radical 3, and that's the shorter side of this triangle right here. I can multiply that by 2 to get 8 radical 3 right here as my hypotenuse for this right triangle right here. And since this is a 45, 45, 90 triangle, this entire side will also be 8 radical 3 multiplied by 2 to get h, or not by 2, but by radical 2. And I'll get 8 radical 6 as my value for h. Another beautiful problem. Simple, right? Simple, but there are some things we have to recognize. The hardest part of these types of problems is just starting to annotate. Annotate everything that you know, and eventually you get to the right answers. All right, Soh Cah Toa, one of our favorite things to do. By labeling your triangle and then using Soh Cah Toa, find the missing side of each triangle. So again, S stands for sine, C stands for cosine, T stands for tangent, O, A, and H stands for opposite, adjacent, and hypotenuse. Opposite angle, adjacent angle between the angle in question and the right angle, and then we know our hypotenuse is h. All right, so for this one, I have the opposite over the hypotenuse. That's going to be our sine. So sine of 30 degrees will be opposite over hypotenuse. And in order to solve for x, I'm going to multiply both sides by a 6. 6 sine of 30 degrees. Then I have this. What is x going to equal here? Well, I have the adjacent side to 60 and the hypotenuse. So I'll have cosine of 60 degrees is equal to x over 5. Therefore, x will equal 5 times the cosine of 60 degrees. Then here I have no hypotenuse, and tangent is the one with no hypotenuse. So I'll have tangent of 45 degrees is equal to x over 10. So x will equal 10 times tangent of 45 degrees. Now, if you know your unit circle or just the common trig ratios that we should know, or it's useful to know, sine of 30 degrees is 1/2. So half of 6 will just be 3. And we know this as a fact because in the 30, 60, 90 triangle, 6 divided by 2 will give us that shorter leg. So making some connections here, hopefully. We know that cosine of 60 degrees is going to be 1/2 as well. So x is going to equal 5/2. And how do we know this is true? Well, this is also a 30, 60, 90 triangle. So 5 divided by 2 will give me that x of 5/2. Tangent of 45 degrees, this one's a little trickier. That's just going to be 1. But we know this as a fact as well because in a 45, 45, 90 triangle, the legs are the same. So a couple things where we can connect trigonometry with some of the Pythagorean theorem things that, or the special right triangles we've discussed. Really fun stuff when we start to connect multiple concepts together. For each triangle, find the missing side labeled x. Give your answer to the nearest 10. So it looks like we're going to be needing our calculator here. So in order to find our missing length of x here, I know that I'm going to need tangent. So I have, tangent of 25 degrees is going to equal 9 over x. Now, I don't know if you've ever learned this before, but here's a little pattern that we notice when we start practicing a lot of math. 8 divided by 4 is equal to 2, and 8 divided by 2 is also equal to 4. Notice what occurred, and this always works. 4 and 2, all that happened is that they switched positions. So what we can do here is tangent of 25 degrees and x can switch positions as well. So x will equal 9 over tangent of 25 degrees. And we can plug that in into our calculator. So if we go to calculate, you can use Desmos as well. I know that's a very popular program that's available on the SAT as well. So that'll be very useful. You can just type it out, 25 degrees. Make sure you are in degrees if you're using a calculator, control enter. And I want to give our answer to the nearest tenth. Nearest tenth means the value right after the decimal. That's our 10th place. So 19.3 looks like what x will be approximately. 19.3. We're not given any units here, so we're good to go. All right, we have 130 degrees as our exterior angle. So we know this is going to be 50 and this will be 40. But we only really need the 50 degrees here. We only need one angle. X is our opposite angle of 50 degrees. And 12 is our hypotenuse, right? Common mistake is that students think 12 is our adjacent side because it's next to the angle. But remember, the adjacent side is always between the angle in question and the right angle. So this would be our adjacent side. So we actually have sine of 50 degrees here is equal to x over 12. And so x will simply be 12 times sine of 50 degrees. Let's see what this is equal to on our calculator. We'll have 12, there we go, 12 times the sine of 50 degrees. Control Enter, and we get 9.2. 9.2 because we want to round to the nearest 10th. Fun stuff. Find the missing values from the triangle below. Ooh, okay, so this time, even in our angle measures, we're given an x, but this is simple. Reminder that in a right triangle, if we have a right angle already, the other two angles will be complementary, right? Complementary angles. Complementary angles are angles that add up to 90 degrees. Supplementary angles are angles that add up to 180 degrees. The way that I like to remember this is that C comes before that S in supplementary. So 90 is less than 180. That's kind of how I like to remember it in alphabetical order. So we know 5x plus x is equal to 90. So 6x is equal to 90 and x will be equal to 15. So if this is 15 degrees, then this will be 75 degrees. So how do we figure out z and y? Well, let's use that 15 degrees. We know sine of 15 degrees will be opposite over hypotenuse. We know that cosine of 15 degrees will be adjacent over hypotenuse. And that's how we can solve. 24 sine of 15 degrees. We'll get some answer here. And y will equal 24 times the cosine of 15 degrees. And we'll get some answer here. Let's plug these in into our calculator. So we have 24 times the sine of 15 degrees. Control Enter. And we also have 24 times cosine of 15 degrees. Control Enter. We get 6.2 for z and 33.2 for y. Is that, oh no, 23.2, sorry, 6.2 and 23.2. Just making sure one more time that that is correct. Awesome. I wonder if I can zoom in on this. That'd be pretty cool if I can, but I don't think I can. Great. Awesome. ABC is a large triangle made up of two smaller right triangles. Find the length of DC to the nearest 10th. So this is what I'm looking for, this question mark. All right. I'm given this 43 degrees. I know that AD is a line that these two triangles within the larger triangle share. So this is also a right triangle or a right angle. So in order to find this H, I know that tangent of 43 degrees will equal H over 18. So H will be 18 times tangent of 43 degrees. Now I can use H to find, let's call this X. I know that tangent of 32 degrees, opposite over adjacent, equals H over X. Now I want to find what X is. And reminder, I can switch places between these two. Always, always, always works. So X equals H over tangent of 32 degrees. Now what was H? H was 18 tangent of 43. So X is going to equal 18 tangent of 43 degrees all over tangent of 32 degrees. And that's what I'll be plugging in into my calculator. Now, some of you might be wondering, Eddie, why didn't you solve for H here? Like, why didn't you just plug that into your calculator? The reason I didn't do that is because we never approximate, we never estimate intermediate values in a problem. And by intermediate values, what I mean is that if you have something like a step in a problem before you get to the final step, that's called an intermediate step. if I get a value from there and I estimate that, then my final answer will be further off from its actual value because we've estimated a previous value, right? So we never approximate intermediate values. We always keep it the way that we see it before we start solving. So we have 18 tangent of 43 degrees all over tangent of 32 degrees, control enter. We want this to the nearest tenth, so we'll have 26.9. And we're good to go. Nice work. Now, calculate the length of BD correct to the nearest hundredth. This is what we want. Now, in order to find x, if I can find this h for height, then I can find x, right? I know that tangent of 49 degrees will equal h over x. And in order to find x, I can flip it. I can switch them. Tangent of 49 degrees. Well, in order to find h, I can use 10, h, and 31. Sine of 31 degrees will give us h over 10. So h is simply 10 sine of 31 degrees. Plug that into that h right here. 10 sine of 31 degrees all over tangent of 49 degrees. And I can plug this in. I want this one to the nearest hundredth. So keep that in mind. The nearest hundredth will be two places after the decimal. So we have 10 sine of 31 degrees divided by tangent of 49 degrees, control enter. We have 4.477, but we want it to the nearest hundredth degree, so we have 4.48. And don't forget centimeters. What a great problem. All right, now that we know how to use Soh Cah Toa, let's talk about some inverse trigonometric ratios. When an angle is missing, we still apply the same Soh Cah Toa process. The only difference is that we need to use inverse trigonometric functions to find that missing angle. So find the missing angles in these triangles below. I know this is going to be sine of theta. This is theta, by the way. Theta. Sine of theta is 1 over 2. Oops, I put 12. 1 over 2. In order to find theta, I'm going to take the inverse sine of both sides. The theta will equal sine inverse of 1/2. And I can plug that into my calculator. This one, I have tangent of theta is equal to 3 over radical 3. So then theta will equal inverse tangent of 3 over radical 3. So this is basically inverse functions, right? Inverse operations, if you want to think about it that way as well. So we have inverse sine this time, oops, right here, inverse sine of 1 divided by 2. That will give us an angle measure of 30 degrees. And then inverse tangent of 3 divided by the square root of 3 will be 60 degrees. And it's kind of cool how this works, because if you think about it, if this is 60 degrees and this is 30 degrees, it makes sense because 1 times 2 is 2. And then if this is 60 degrees, I'm going to divide by radical 3. And 3 divided by radical 3 is radical 3. So kind of cool how we're using our special right triangles to prove that these inverse trigonometric functions do absolutely work. All right, let's try out some practice problems. ABCD is a trapezoid. Calculate the size of angle ABC. So I want this entire angle right here. I want this entire angle, but I know right off the bat that if I split this up, I have 90 degrees right here. This is 90 degrees. Then I also know that because this side is 12 and this entire side AD is 20, I know this little side will be 8 centimeters. I'm also aware that if this is 15 centimeters, then this is 15 centimeters. And guess what? This is our special right triangle, 8, 15, 17. But really what we wanted to know is this angle right here. I'll put it in green. I want to know this angle. Because if I know theta, ABC will equal theta plus 90, right? From 90 from this blue. So this theta will be tangent of theta is equal to 8 over 15. Theta will equal inverse tangent of 8 over 15. Let's figure that out and also add 90 while we're at it. So we have, oops, I just want trig here. Trig, inverse tangent of 8 divided by 15. And on the outside, I'm going to add a 90. That gives me 118, and it doesn't tell me what to round to, so I'm just going to round to the nearest whole number here. We'll have 118 degrees right here for ABC, approximately. In triangle ABC, the length BC is 70 degrees. BC is 70 degrees of the length of AC. So whatever AC is, BC will be 70% of that, 0.70 of x, which is the same thing as just 0.7, right? For those of you that might struggle with percentages. And so let's find the length of angle BAC. Well, that's just going to be tangent of theta since we have the opposite and adjacent sides. 0.7x over x. Guess what? The x's cancel out. So theta is just inverse tangent of 0.7. How convenient. So we have inverse tangent of 0.7. Control Enter. That's about 34.99. I'm going to round that up to 35. 35 degrees, squiggly, 35 degrees. Here's another one. Find the size of angle X. I'm given that the area of this smaller triangle is 15 centimeters squared. What did we say the area of a triangle was? 1/2 base times height. Now the base, let's say, is 3. We don't know the height, and that's equal to 15. Divide both sides by 3 and multiply by 2. H gives us 10. So this is 10 right here. Now I can figure out what X is, because 10 is the adjacent side and 26 is our hypotenuse, right? Adjacent, hypotenuse. That means we're using cosine. Cosine of x is equal to 10 over 26. Fun fact, this is a 5, 12, 13 triangle, 10, 24, 26. So x will equal inverse cosine. We can simplify this a little bit, 5 over 13, and that will give me the size of angle x. Inverse cosine of 5 divided by 13. That will give me 67.4 degrees. When in doubt, round to the nearest 10th, whole number, 100th, as much, whatever you'd like. In this problem, they'll probably tell you round to the nearest 10th or 100th or nearest whole number. Similar triangles. Let's get it. I believe this is our last topic. Let's lock in. So whenever we see similar triangles, my biggest suggestion to you is to redraw the two triangles that you see. So if I redraw these triangles, A, C, D, and the bigger triangle, A, O, B, I can figure out which sides are proportional to each other. This is X and this is 10. This is 15, and that's how we can prove that AO is not 12. Biggest mistake that students make is they say AO is 12, but it's actually 12 plus X because you have to combine these two sides. And now we can set up a proportion. X is to 10 as 12 plus X is to 15. Let's use our little butterfly method, or some of you know it as cross multiply. So we have 10 times 12 is 120, 10 times X is 10X. X times 15 is 15x. That should be an equal sign. So 5x is equal to 120, and x is equal to 120 divided by 5, which is 24. Kobe. Whenever you see multiple triangles in a diagram, redraw the triangles. Redraw the triangles. Here we go. So the first thing I do before I even read the problem, redraw the triangles. Well, I mean, I do need that AB is parallel to DE here to know that we can use these proportions. So the smaller triangle here is CED. We have 4 and x plus 2. My bigger triangle is CBA. And again, these are just sketches, right? You don't have to worry about being so accurate. 4 and 12 add up to 16. X plus 2 plus 5x minus 4 is 6x minus 2. And now we can create a proportion. X plus 2 is equal to 4, or is to 4, as 6x minus 2 is to 16. Cross multiply. We got 16x plus 32 is equal to 24x minus 8. Let's go ahead and solve. X is equal to 5. Just like that. In the figure below, solve for x. Again, redraw, right? Redraw. Let's put some values here. A, B, C, or D. Let's label these points. So I have one right triangle. This one's going to be, I want to solve for x. So I have x here and 2. So I have A, D, B. Now let's think about what we know here. We know that 2 is the shorter side, shorter leg of ABD. I can draw the bigger triangle similarly. This is x, and my hypotenuse will be 2 plus 5, since I have A, B, C. So x is to 2 as 7 is to x. All right, let's go ahead and cross multiply. X squared will equal to 14. X will be positive or negative square root of 14. But since we're talking about distances here, cannot be negative. So x equals radical 14 is our answer to this problem. Here's another one. In the right triangle below, BE is equal to 5. So this is 5. AB is equal to 12. All this is 12. And angle DEB is a right angle. Great. That's good to know because these all have to be right angles. If the length of segment AC is 1 unit more than twice the length of DE. So let's call this DE x. And so AC will be twice the length and 1 more than that. What is the length of segment DE? So I'm looking for what x is. Great. I'm glad I made DE into x. So let's draw that smaller triangle, DEB. I'm given x and 5. Now, in the bigger triangle, this will be CAB. And notice how I keep the B's the same here on the same side. For every triangle that I've drawn so far, I've tried to keep it proportional. And that just takes practice. So hopefully these are giving you good practice here. AC is 2x plus 1. AB is 12. So I can create a proportion. X is to 5 as 2x plus 1 is to 12. Let's go ahead, cross multiply. Don't forget to distribute completely. And boom, there's your answer. X is equal to 5 over 2. Simple as that. Simple arithmetic once you're able to set up the problem. All right, let's take a look at this one. In the figure below, triangles ABC, ABC. So let's redraw that. ABC and FEC are similar. Great. So that means AB and FE are parallel. Triangles DCB. Let's redraw DCB here. And FEB are similar. So FE, again, right here, FE. These are parallel as well. Given that AB is equal to 9, DC is equal to 12, find the length of EF. So this is our X. And guess what? We can create a proportion here, but we don't have another side. So what should we do? Let's make it up. Let's say this is A and this is B. Then this is A and this is B. So what do we have? We have X is to A. X is to A as 9 is to A plus B. Let's check out this one. X is to B as 12 is to A plus B. So what can we do here? We can maybe add x over A plus x over B. We can also multiply both sides by A and B and then solve from there as well. What's another thing we can do here? Let's try adding them. So x over A plus x over B. What will this give us? This will give us bx plus ax all over A plus B. That will give us, if we factor out the x's on top, A plus B over A plus B. I was buffering there a little bit. So this is just equal to x. So what did we just find? We just found that if we add 9 over A plus B to 12 over A plus B, we're just going to get the value of what this x is going to be. Okay, great. Another way we could have set this up, by the way, is we could have said 9 is to x. 9 is to x, or x is to 9 actually. The smaller to the bigger. X is to 9 as a is to a plus b. And we could have said x is to 12 as b is to a plus b. And then we actually get a very much easier answer here. We know that if we add a over a plus b to b over a plus b, we get 1. So we know that x over 9 plus x over 12 is also equal to 1. And that actually becomes way easier. We get 12x plus 9x is equal to 9 times 12, which is 108. And that gives us 21x is equal to 108, and x is equal to 108 over 21. Now, 108 and 21 are both divisible by 3, and that gives us 36 over 7. Now, we did go kind of a loop-de-loop around way to get this, but once I figured this out, and I got to that, oh, these add up to whatever we have on top, I decided, oh, what if we switched up the order in which we set up this proportion? Then we get straight to this. All right, let's try out this problem. 3 similar triangles are placed in the formation shown below. MN is the perpendicular bisector of CB. So this length right here, CM to MB, will be equivalent. Now, I'm given this information and calculate the length of CB. So I want the length of this entire thing. Well, I know that this 6 and this 4. I also need to know some more information here, right? I believe that we will have, let's see, what can we do here to find the length of CM and CB? I know that all these triangles are similar. So we have 6 is to 4, but without, oh, I believe I should have put a 3 here as well in the problem. There should be a 3 here for EB. So if EB is 3, then I have 4 is to 3, or actually, this might be a 3 here. And I think this 3 centimeters here should be a kind of a distractor, and students might think 3, 4, 5 here as a mistake. But because I know this is 4 is to 3, if I redrew this smaller triangle, I have BED. We had a bit of a crisis situation there, but it's all solved now. DE is 3, BD is 4, and I have this larger triangle here, NMB, NMB. This is 6, and we want to know what MB is, because the length of CB will be 2 times x. So if we have 4 is to 3 as 6 is to x, I get 4x is equal to 18 by using the butterfly method or cross multiply. So I get x is equal to 18 over 4, which is 9 over 2. I can plug that in here, 2 times 9 over 2, to get 9 centimeters. Phew! Very nice. And that's it for all types of triangles. Everything you need to know about triangles on the SAT within 1 hour. I hope this helped. If you found this video useful or learned something new, make sure to like and subscribe. Another reminder to click on the link in the description below to get access to the 30 practice problems on the SAT. If you want to see anything else from me, comment down below, and I'll see you next time.